This is the last lecture for the classical mechanics. We will derive the Lagrangian density function for the electromagnetic interaction that reproduces the Maxwell's equation in a covariant way. In the previous chapter, in chapter 18, there are problems 18.7 and 18.8. In the Heaviside Lorentz unit system, Maxwell's equations for the two cases, divergence equals rho and curl B. So this is the Gauss law, and the second one is Ampere-Maxwell's law. Is expressed like that. This complicated vector equation were reproduced by the covariant form, where around mu f mu nu is 1 over c j nu. This is completely covariant expression, and f mu nu is field strength tensor round mu a nu minus round mu a nu. The remaining two equations that there is no magnetic monopoles, and Faraday's law is expressed as an equation round mu f dual mu nu, where f dual is obtained by multiplying Levi-Civita tensor to the field strength tensor. So let us assume that you have solved these problems and make use of the fact that the most important Maxwell's equations are expressed in the covariant form. Let us go back to the least action principle, in this case too. Action is the integral of Lagrangian with respect to time. And actually Lagrangian can be re-expressed as an integral of the space over the space. And now this function is expressed as a Lagrangian density function, because electromagnetic field is distributed all over the space and time. So least action principle applies to this case. In this case, we have to field equation. In that case, the Euler-Lagrange equation should be expressed as a variation of the field fluctuation. That field is the electromagnetic field that A, Bohr vector. So A nu is each component of the photon field, A nu, and in the case of point particle, we have time derivative and velocity. This Lagrange equation is the variation for the time variable where the fundamental variable was time only. But in this case, this variation of the field is not with respect to the fundamental variable t, but that includes the time and spatial variable too. So this time derivative is replaced by covariant form for the space-time variable. And for each, this is time and time. So in this case, mu equals 0 is time and time, and x component is 1 and 1, and y component is 2 and 2, and z component is 3 and 3. So that's the difference. And x is the position of the vector, but this is the field, electromagnetic field itself, that has a vector quantity, and so each vector quantity must satisfy this equation. Alright, we assume that you understand this Euler-Lagrange equation for the field. Then we want to construct a Lagrangian that satisfies the Maxwell's equation that we have already derived before. Alright, so we have the equation of motion, and this equation of motion must be the same as the Euler-Lagrange equation that is obtained by some Lagrangian density function. From this case, we assume that there is no current at all. no current at all. And actually, if there is current, equation on the right side becomes J nu, because this is the only derivative that is related linear to the vector field, vector potential. Lagrangian must be corrected by just J dot A, because A does not appear anywhere else. So that extension is trivial. So our main concern in this step is just ignore the J part and find out the Lagrangian that reproduces the Maxwell's equation. Okay. From this, I have a derivative, and there is a field strength tensor, and that is just like conjugate momentum. So conjugate momentum should be the field strength tensor. Okay. Lagrangian partial derivative with respect to round mu a nu should be proportional to f mu nu. Alright, suppose Lagrangian is proportional to round mu a nu times some constant function. In that case, if I take the derivative, then b is independent. So if I take the derivative with respect to round mu a nu, then the answer is b mu nu. However, b mu nu is identified to be f mu nu, and f mu nu itself includes round mu a nu. So this is not the exact answer. But we find that it is related to something like should be f mu nu. So let me just try as a second step that Lagrangian is round mu a nu times f mu nu. But we know f mu nu is anti-symmetric, so I can add minus f nu a round mu a nu and divided by 1/2. That is exactly the same as the original value. And actually that is the Lorentz scalar too. So if I use this expression, then it becomes 1/2 f mu nu f mu nu. This is a Lorentz scale. Alright, so why don't we make use of this f mu nu to find the conjugate momentum? Then this term appears here twice. So there are 4 ways to obtain this kind of term. So I have factor 4, and for each alpha and beta, I have this kind of derivative. So this derivative is non-zero and actually 1 only if alpha is equal to mu and beta equals mu. So the answer is 4 times f mu nu. So if Lagrangian is 1/4 of f mu nu, then the conjugate momentum is f mu nu times something. So because we have determined the Lagrangian from the equation of motion, which is homogeneous, we do not know the value for the lambda. So as we have done in previous case, we would like to obtain the Hamiltonian. In this case, this is Lagrangian density, so Hamiltonian should also be computed as a Hamiltonian density function. So from our trial solution that is 1/4 lambda f mu nu, we would like to extend the interaction with the matter, and I just briefly explained that this guy must give J nu, then Lagrangian must include the term like J dot A, something like that. The detailed over factor is actually -1 over C A dot J, but it is your homework to find this over factor exactly. And if you compute the Hamiltonian density function, your final result will be expressed like that: -1/2 lambda and electric field squared plus magnetic field squared. You know, 1/2 electric field squared plus magnetic field squared is the electromagnetic field density. in vacuum. So I think it's good to have the Hamiltonian as the energy density of the electromagnetic field, so lambda is determined to be -1. And additional p's is there, but if you integrate over the whole space, this guy rapidly decreases faster than the area of the surface. You just consider very large sphere, and as r goes to infinity, this guy disappears on the boundary. So finally, our Lagrangian density function for the electromagnetic field is -1/4 f mu minus 1 over c j dot a. This guy gives the correct equation of motion for the electromagnetic field that is called Maxwell's equation. Okay. Again, we have found that this j dot a is Lorentz scalar, and f mu is Lorentz scalar too, and this guy is invariant of the gauge transformation. Okay, that's it.